So most people are already somewhat familiar with the terms black holes and wormholes, so what I'm going to do is give a very, very basic overview of what the terms mean, and then talk more about them, and then talk about how they might be useful, for example, in time travel, etc. So basically, black holes are the densest object in the universe with the strongest gravitational pull. So what most people know about black holes is that nothing, not even light, can escape. And a wormhole is basically a type of a tunnel with black holes at either end that leads to another part of the universe. So sort of like what Christy said about multiverses. So basically, a black hole can be compared to a giant whirlpool. So the pull of a black hole is not as strong from further away, but the closer you are, the stronger the pull is. So, for example, if you're a fish, if you swim fast enough, you might be able to escape the pull of a black hole, of a whirlpool if you're going fast enough. And the same is true for a black hole. However, unlike a whirlpool, for a black hole within a certain zone, nothing can escape. That is called the event horizon. So in this artist's rendition of a black hole, so the black hole part is the black hole. And basically the event horizon would be the very edges of the black hole, and anything, including light, that falls into past that event horizon can never escape. That's why it appears black to us. And so how does a black hole work? So it works, the pull is created by gravity, and the more matter there is, the stronger the gravity. So light itself is affected by gravity. So, for example, imagine the yellow line is light. So as light passes by very massive objects, it bends and changes direction. So the more intense the gravity, the more the bending of the light. And a bit about general gravity. As we all know, gravity is the thing that causes things to fall towards the earth, like apples. So if you throw something, it will fall. If you throw it harder, it will fall further away. So let's say you're on a mountain with a cannon, and if you shoot a cannonball fast enough, it might be able to go into orbit around the Earth, or Newton thought so. And if the cannonball achieves a fast enough speed, it might be able to escape the pull of the Earth's gravity entirely and go wandering off into space. So the velocity needed for how fast something has to go to escape gravity depends on the strength of the gravity of a planet. And for a black hole, the escape velocity is greater than the speed of light, which means nothing can escape, since nothing can move that fast, and that's why light falls into a black hole. Now, how black holes form? They form when a star dies. So when stars run out of fuel for their nuclear reactions, the center of the star cools, compresses, and caves in. And as it caves in, it crashes against itself and rebounds in an explosion called a supernova, as you can see behind me. So basically, a supernova might form a black hole if the original mass of the star is 25 to 40 times the size of the sun. So what happens is what remains of the star's center goes into a sudden collapse called fallback, and the star self-plunges inward under its own weight and contracts tighter and tighter until everything is destroyed, including its atoms, and forms a single point of extremely dense mass called a singularity. And that's part of what makes up a black hole. I'll talk about singularities in a moment. So basically, what defines a black hole is something with a high enough density within a critical radius, also called the Schwarzschild radius. So this is the Schwarzschild radius. It's the object's mass times twice the constant of gravity divided by the speed of light squared. And so, yeah, that's really mathematical. So actually, I'll just talk about black holes then. So a singularity is this thing you see in the center with an arrow pointing to it. It's basically a massive amount of densely packed matter at the center of a black hole. And it's so densely packed it is a single point, smaller than an atom, but it contains the mass of a star. So basically, at a singularity, the laws of science and the ability to predict the future break down. And so it's like the Big Bang at the beginning of time, except the singularity would be the end of time. So if time's already ended, why are we still here now? Why are we alive? So a singularity does not affect anyone outside a black hole, because nothing, no information can reach people outside the event horizon. And back to event horizon, that's, as I mentioned before, the point of no return. Nothing can escape. So it surrounds an extreme gravity zone. So let's say you are a beam of light. Just outside the event horizon, your energy would allow you to continue forward, though you would bend towards the black hole. Now, if the light crosses the event horizon, then it would curve inward in a spiral, getting closer and closer to the center of the black hole. And as it gets closer to the singularity, more gravity redirects it inward, so it continues spiraling downwards until it reaches the singularity and is destroyed. And that is why light in a black hole never returns. And so it can't reach eyes or a telescope, so that's why black holes are black. Now, it's not just empty space inside an event horizon, even though black holes look black. There's actually lots of light inside a black hole. It's just not visible because gravity keeps it contained. So now, we were thinking about black holes in 2 dimensions. Now I want you to think about it in 4 or 3 dimensions. So, a quick video. Are you?
We tend to think of space as rigid and stable, but Einstein proposed that space and time are woven together in a flexible fabric. Massive objects like the sun actually bend and warp the fabric of space-time, creating troughs that smaller objects can fall into.
What actually happens is matter warps space-time. So the very space, the 3-dimensional space that we walk through, warps slightly. Every time when I walk through space, space around me warps in on me ever so slightly, but because we're not very massive, it's so minuscule that we don't sense it.
If an object is massive enough, like the Earth, it will warp space-time so we can sense it and fall towards it. That's gravity. But what happens if an object is much, much more massive than the Earth or the Sun? In theory, it could warp the fabric so much it would create an actual hole in space-time. Once something fell in, it couldn't escape. Not even light itself.
So imagine a place where the gravity is so strong, turning on a flashlight. The light would go up and it would never leave. It would curve and come back down just the way a tossed ball on Earth is not traveling fast enough. It goes up, curves, and comes back down.
Space itself is falling inside the black hole. It's rather like a river falling over a waterfall. It's like that, except it's space itself is falling over the cliff. There's a place where the space starts moving faster than light. So the light, which is trying to get out, it's rather like a kayaker trying to make their way upstream on a river that's going too fast. They get dragged down to the center of the black hole.
Gravity becomes a riptide. The closer you get, the stronger the current. Eventually, you reach the event horizon, the point of no return. Deep inside, whatever goes in is lost in a point of infinite density.
The matter goes inside the surface of the black hole, shrinks down to the very center, where it gets destroyed in a region of infinite warp space and time, and it's gone.
And so, it seems, are the laws of physics. At the center of a black hole, all equations break down. Even for physicists, what happens deep inside a black hole is a mystery.
Okay, so basically what that video told you is that space can stretch, crunch, bend, and warp. And so this is a picture of the Earth and the Moon in the fabric of space-time. So as you can see, the Earth leaves a deeper indentation in the fabric of space-time. So the indentation is the gravity zone around the object, and the deeper the dent, the more energy is required to leave. So a black hole would be like this. So the singularity at the bottom would be a very tiny but very dense object and heavy object on the space-time fabric, since it's a lot of mass squeezed within a critical radius. So within a certain radius, it will warp space-time completely around itself. So to put into perspective how dense it must be, so if the sun was the size of Mount Everest, it could create a black hole. And this is, the arrows pointing to Earth, so Mount Everest is smaller than that. Okay, so now, what would happen if someone, like a human, fell into a black hole? So, firstly, spaghettification, also known as the Newton effect. So, it would force your body into a long, skinny, stringy shape, like spaghetti, and then you die. So, within an event horizon, and this is purely hypothetical now, so time would pass slower for you, and it would seem like the outside universe is aging more rapidly, and you could see stars visibly changing as they age and die. Red will be the last color you see before time stops. And if an astronaut falls into a black hole, the energy equivalent of the mass of the astronaut is returned to the universe in the form of radiation. So, in a sense, you'd be recycled. But that would be a poor way to be immortal because you'd be dead. So, some examples of black holes would be Cygnus X1, which is 6,000 to 8,000 light years away. It's one of the smallest known black holes and one of the first black hole candidates. NGC 4486, also called Virgo A in the M87 galaxy. It's supermassive, one of the biggest, and it's 3 billion times the mass of the Sun. And the distance from one end of the event horizon to another is the same size as Pluto's orbit. And my personal favorite, the Milky Way black hole, also called the Sagittarius A star. It's a black hole 4 million times the Sun's mass in the center of the Milky Way, which is our own galaxy. It's in the constellation Sagittarius, and it's 27,000 light years away. So now that you know there is a black hole in the center of our galaxy, how likely is it that we're going to die? It's very likely you're going to die, but not by black hole. So because with what we know about black holes, and there's a lot we don't know, there is no black hole currently close enough to us. And the Sun itself won't turn into a black hole when it dies because it's not big enough. So, well, I wasn't going to put in a pun about black holes, but how could I resist? I'm sorry. Okay, so wormholes. What is happening? Yeah, okay. I hate technology. So, a quick video on
Cosmos spaceship. A theoretical tunnel providing shortcuts through space and time. The Einstein-Rosen mathematical wormhole arose from studying black holes. A black hole is a region in space of extremely strong gravity. The gravity is so strong that there is no way for objects that get too near to break away from its gravitational pull. Nothing can escape a close encounter with a black hole, not even light.
Return.
But Einstein never intended his wormhole as a tool for space travel.
Ignore that part.
His wormhole is theoretically created at some moment of time. It opens up briefly, then pinches off. Anything that tries to pass through it will get crushed when it's squeezed.
Oh, okay. Well, it's gonna get crushed and then it dies. Okay. Wait, does it? Yeah. Cool. Okay, so basically what the video says is that if something goes into a black hole, a wormhole, it will get crushed and dies as the wormhole breaks apart. So wait, let me see if I can do this.
Time. It opens up briefly, then pinches off. Anything that tries to pass through it will get crushed when it squeezes apart.
Yeah, basically. So basically wormholes may or may not exist, but from Einstein's equation, it would appear that every black hole has two ends. So if you go through a black hole, you could be led to a different region of the universe if you don't die first. And so a wormhole is basically a shortcut through space and time, so space-time. So how do wormholes form? So a dimple in space-time is mirrored by another dimple elsewhere in space-time. So two dimples grow and join to make a tunnel, and that would be a wormhole. And there's a black hole at each end connecting the two universes. So even if wormholes do exist, what would be the use of them? So time travel. So the general theory of relativity says that space and time are dynamic. So basically, space-time could be so warped, you could go on a spaceship and be back before you left. So what wormholes does for this is they are space-time tubes that act as bridges between space and time. So journeying through a wormhole can take you to a different place as well as a different time. So think about a piece of paper. So if you want to draw a line from one edge of the paper to the other edge, there's a speed limit to how fast a pencil can move across a piece of paper. Now, how the paper changes is a different matter. So for a wormhole, a shortcut is made by warping space, for example, folding the paper, to connect two points that were separated. And that's how a wormhole works. And also, to add on to what Christy said about multiverse, the other end of a space-time wormhole could be in a different universe entirely, a parallel universe that exists alongside ours in hyperspace. So the last bit would be black holes. So, oh no, not this. So if a spaceship cruises near a black hole, time can be slowed to any speed desired. And if you fly by an event horizon, you would be able to see time stand completely still. However, black holes are not a nice place for humans. But it might be possible to do time travel in a supermassive black hole, so large that the tidal forces associated with them would be survivable, and it would have to be large enough to travel through without becoming spaghettified, and that's not very likely. But anyway, to end things on a happy note, here's a picture of the Milky Way, and there's that black hole right in the middle of it. So good luck and don't die in a black hole. Thanks.